let's continue. Let me open the table of content first. Okay. Hopefully my internet connection is fine. Let's see how it goes. Okay, we are still on chapter 28. Still on homework simulation here. Now let me open that. Okay. We are still in this section, homework simulation. Okay, if I remember correctly, the last time we take a look at this question 4. Now let's look at this question 5. Test and set. Let me open this. Thread log. Now let me open the simulator first. Okay, this one. And now let's take a look at test and set. Okay, atomic swap of 1 and mutex. Okay, wait, first try to understand the code. Okay, we use the XGSG instruction to put a simple logging primitive. I assume XGSG instruction here is for atomic stuff, atomicity or something like that. Basically, either we do everything or nothing, I guess. To put a simple logging primitive, how is the log acquire written? How about log release? Okay, the log acquire written. I am still not sure about the atomicity, I guess. Yeah, this one, atomic swap of 1 and mutex. Okay, test if we got 0, log is free. Oh, wait a minute. So we test the register AX. Interesting. Now how do this work again? Is it from this to this? This is the operation code, okay. Need to argument, parat by comma, okay. Atomic exchange. Yeah, how are we gonna do the atomic exchange? Fully specified atomic exchange. Get arc. Okay. So maybe take a look at this. Time here. Okay. Alt. Oh, wait a minute. Is it like test and set? Maybe. I mean, from the file name, it looks like it is test and set, right? Which we take a look previously. Test and set. I think this one, right? So basically we replace the value in the pointer with new value, or maybe memory address, something like that, with new value, and then return the old value. So maybe that's what happened here. Old, right? Similar to this. And then this one looks like we are replacing the value in the memory with the value in the register, and then put the old value in the register. Maybe something like that. What is it called? Replace the value in memory with new value, something like that, and then put the old value, maybe put the new value in memory, and then put the old value in register. The old value is from memory. Maybe something like that. Extract old value from memory, and then put new value from register in memory, and then put old value in register. Maybe that's what's going on in this instruction. So we have, what is it called? We have old value in the AX. I guess during this instruction we suppose we have, I think we have the new value, right, in this register, and then putting that in the mode text variable here, and then putting the old value back into the register here. So what we check here should be the old value in the mode text, maybe something like that. Maybe. Okay. Yeah, I'm kind of curious how that works. Well, let's try that, I guess. Using the default value, the default flag maybe. Treat logs. The program. Treat logs. Test and set. Memory, mode text and count, and then trace the, what is it called, the register AX and PX. Should I put the code tracing to? Maybe. maybe something like this. Okay, I mean, to answer this question, how about lock release, right? I'm assuming because we didn't use atomic operation for the lock release, right? Maybe we will have some problem again, the non-mutual exclusion. Maybe. I mean, I'm still not sure. Okay. XGHG, something like this. Text become 1. Okay. AX become 0, right? Because again, we move the new value from AX into this mutex, and then putting the old value from previous mutex here into AX here, right? Then we check that if AX is 0, if it is not 0, right? If the value in AX not 0, we are going back to acquire label here, this label, which means what is it called? We maybe put the lock, something like that. I mean, maybe. I mean, if the old value is not 0, right, it is most likely gonna be 1. So that means the new value might be 0, maybe something like that. Square. Okay, and because the value in AX is 0, right, we are not jumping back into the acquire label and then move count into AX. Okay, entering the critical section here. Okay, start it back in here, and then release the lock, right? Doing some iteration, and because it is greater than, right, we didn't jump back to the top level. This one, basically, I think running this again, we are not jumping back to this and halt here and continuing to halt. It's the same for this one. Okay, yeah, I'm kind of curious about the release one. Maybe let's add interrupt. Every 3 instruction maybe. Let me try. So every 3 instruction, this one test, right? Okay. Alright, move that. Test AX1. Oh, wait a minute. Okay. In this case, AX is 0, right? Because the old value is 0. And then in this case, in the thread 1 case, AX is 1, right? So thread 0 is continuing to the critical section here, right? Meanwhile, thread 1 keep, what is it called? Keep going back into the acquire label here. Because again, the value or the odd value in mutex is still 1 during this time, right? During the test here. It's still 1, so the value in AX still 1, 2, right? That's why we jump back into the acquire label here. Okay, and then that 0 keep continuing in the critical section. Okay, this one, oh, after, what is it called? We are releasing the lock here on thread 0, and then, well, because we didn't execute this, what is it called? Atomic operation after we release the lock from thread 1. That means the threads, the thread 0, not thread 1. I get confused there. Okay, we release the lock from thread 0, but the thread 1 didn't realize that we already released the lock, maybe something like that. So we keep going in the thread 1 in this case. We are going back into this acquire label, something like that. Okay, and then halt, and then check again. Now the thread 1 already know that the lock is, what is it called? The lock has been released. So thread 1 is not spinning anymore and entering the critical section and do the rest. Okay, but yeah, maybe that is the, what is it called, the problem, maybe. Like again, what is it called? That 1 didn't realize that the lock has been released, right? Unfortunately, we have, what is it? We have frequent interrupt, so the looping is not that long, the spinning is not that long, maybe something like that. If I remember correctly, the book talk about that. Is this the one? Maybe not. Okay. Oh, Wait, release. No, not that one. Yeah, it's near the end of the book, if I remember correctly. I think this one. What would happen if the release of the catalog came after the park and not before? Maybe that what happened. So the release of the lock came after. Oh, but this is park. Yeah, basically instead of spinning we put the thread to sleep, right? So it causing the thread to sleep forever, potentially, because the thread didn't realize that the lock has been released and keep waiting. But maybe that's kind of the same in this case. The thread 1 did not realize that the lock has been released because of the interrupt here. So it at least been one more time, right, to check. If we increase the interrupt here, interrupt frequency, instead of 3, maybe something else. We might have the chance to keep spinning. Maybe. But yeah, this is kind of interesting to see that the lock has been released on thread 0, but another thread didn't realize that. Okay. How about lock release? Yeah, there's a potential that another thread might not realize that the lock already released because of interrupt, right? So there is something to keep in mind. How is the lock acquire rate then? The lock acquire rate then, well, it is test and set, right? So how to explain this? Basically, we put the new value into the mutex, I guess, or the log, and then get the old value from the log and test that. So we are testing the old value. Is it already unlocked or still locked? And then if it is unlocked, then that means we already acquired the lock. Something like that. Check if the old value is unlocked or locked. If the old value is unlocked, that means current thread get the lock. If the old value is locked, that means current thread did not get the lock yet. So we are checking from the old value, if I understand correctly, how the log acquire written. Okay. Now run the code changing the value of the interrupt test I again and making sure to loop for a number of times. Does the code always work as expected? Does it sometimes lead to an inefficient use of the CPU? How could you quantify that? We already changed the interrupt interval. Now let's try adding more iteration by changing the iterator, I guess, iterator value. Previously the initial value of the iterator or bx here is 0. Now let's try to increase that to 2 maybe and see how it goes. Okay. Alright. Entering critical section. I'm still checking. Okay. Alright, I already released the log here. Still checking. Going back to this one, acquire label. Right. Still iterate. Oh. Okay. Trying to get this one. We're going back to the acquire here. Right. And then interrupt. And then what is it called? Put the mutex value, something like that. The atomic operation here for the log, and then test that. Okay, because ax is 0, that means that 1 get the log, right? So we are not going back to acquire label here. Okay, this one. Okay, I think this one is gonna going back to acquire label. So we are checking if the log has been released or not, right, in the thread 0. And then that one entering critical section here. That 0 still checking if, what is it called? If the log has been released or not. The log has been released here. And then testing again. Testing the iteration, I mean. Okay. And because the test is before we release the mutex, that 0 is going back one more time, right? Oh. This is interesting. One more time, okay. And this one also going back to the top label here, basically running this again from the acquire. Okay. Now what would happen here if input thread got interrupted during this atomic operation. Okay, the out value is 0 for AX. And then okay, wait, you know what? Let's also add the header. Every 6 instruction maybe. Where is it? I think this one, right? Okay. Yeah, this is the one that I'm curious. We get this, right, doing atomic stuff, and the previous, what is it called? The previous value of mutek is 0. The old value of mutek is 0, right? And then we are also checking this in thread 1. And the previous mutek value become 1. Okay. So that means thread 1 will be, what is it called? Will keep spinning, waiting for the lock to be released, I assume. Okay. For thread 0, we are entering the critical section here. For thread 1, still spinning, right? Okay, and alright, release the lock here. Now thread 1 get the mutex because the old value is 0, right? From this one. Okay. And then thread 1 I assume will stop spinning to check the log. Okay, this one checking the iteration, right? And then thread 1 going into the critical section to add the value into count. Thread 0 half, the rest is thread 1. Okay, so in this case, maybe the inefficiency is that, yeah, in the interrupt every 3 instruction, something like that, with the, what is it called, with the 2 iteration. Maybe the inefficiency is that each thread will keep spinning once, because by the time another thread release the lock, the current thread didn't update the value of the thread, of the mutex, I mean, of the lock. So we are testing the previous state rather than the current state after another thread release the lock. So the current thread didn't know that the lock has been released and keep going for one more spin until they finally until the thread finally realizes, oh, the lock has been released. So they enter the critical section. And that, what is it called? And that apply for thread 0 and thread 1 in this case. Yeah, this one tests, right? But this one has been released. What is it called? The lock has been released. So maybe there is two scenario. Current thread test the lock has been released or not after the lock has been released, which means we are checking the, what is it called? The previous state of the log instead of the current state from another thread. Instead of the current state of the log. And then the second scenario is that current thread test the log has been released or not before, or maybe right before the log release from another thread. Which means the current thread going into another spin. I mean, both of this is gonna go into another spin to check the log, right? Okay. Previous state of the log instead of the current state of the log. Yeah. The current thread going into another spin to check the log. At least from this scenario, right? So testing here, the interrupt with the, what is it called? The correct timing, I guess. Interrupt in the correct timing will make the thread spin again because the thread did not realize that the lock has been released from another thread. And if we have multiple thread or more than 2 thread, then a lot of thread gonna keep spinning maybe something like that. So the interrupt here can mess up the, what is it called? Can mess up the execution, I guess, or can make the thread keep spinning. Maybe that's the right word. Maybe. Yeah, I'm still trying to understand this. This is a new concept for me. Okay. Does the code always work as expected? Well, maybe not. I mean, again, sometimes the thread going into another spin to check the log, right? Maybe that's not what we expect. Does it sometimes lead to an inefficient use of the CPU? Maybe. I mean, instead of going directly into the critical section, right? The thread going into another spin to check the log, and that may cause inefficient use of the CPU. Maybe. How could you quantify that? I am not sure how. Yeah, how do we quantify that? I'm still not sure yet. Okay, use the test B flag to generate specific test of the logging code. Test B flag to generate specific tests of the logging code. For example, run a schedule that grabs the log in the first thread, but then tries to acquire it in the second. Does the right thing happen? What else should you test? Oh, right, we can manually, what is it called? I think we can manually control which thread run when. Oh, okay, that looks fun, I guess. Let me check. Do we need to provide interrupt frequency? Probably not. Maybe. Okay, yeah, let's leave this be, which means we are using 2 iteration. Let me check the readme. Okay. For 2 instruction, then thread 0 for 3, then repeat. Let me check. Okay. Maybe if we always have interrupt in here, right? What would happen? Every 2 instruction, so running 3 instruction on thread 0, and then running 2 instruction on thread 1, and then interrupt that. Let's find out, I guess. Okay, maybe something like this, and then the header every 5 instruction. release. We check here. Okay, add. Alright, into the critical section. I assume this will going back to the acquire. Okay, we release the mood text here. Oh, okay. What is it called? We are going. Okay, we check, right? We get the mood text here, and then this one just enter the acquire state. Okay, test, right? Okay, going back. Oh. Okay. Maybe this is more efficient, or maybe the same. I mean, yeah, by the time we release the mood text, right, the thread one just gonna check if the mood text has been released or not. So we are not doing another spinning, another, what is it called, redundant spinning to check the log. Okay, and then this one checking the log, right? And it looks like the log has been acquired. Okay, and then that one just enter the critical section here. So this one will, what is it called? This one will going into another spin, and okay, right, another spin, test. Okay, thread one just release. Oh, okay, yeah, maybe this scenario, maybe current test, the log has been released or not read before the log release from another thread. So the test here on thread 0 is done right before the log has been released on the thread 1. So maybe we have one redundant spinning on thread 0, something like that. And then we check again on thread 0. This one iterate again. Okay. We're going into the critical section here. Okay, this one starts spinning from the top, right? Enter in critical section and release the mood text. And then, right after releasing the mood text, thread 1 coincidentally check if the mood text has been released or not. And it looks like the mood text has been released. that 0 checking the iteration, the thread 1 moving into critical section, that 0 halt, and then that one continuing. Maybe, but then again, yeah, maybe this one is likely efficient, because instead of having two redundant spinning from thread 0 and thread 1, we have only one redundant spinning on thread 0. But then again, I'm not sure if we increase the iteration, right? If we increase the iteration, is it gonna be different? Yeah, I'm still not sure about that. But for these two iterations, it looks like this pattern might be more efficient than having the interrupt every 3 instructions on each thread. Maybe. Okay. But I'm kind of curious too. Okay. But then tries to acquire run schedule that grabs the lock in the first thread, but then tries to acquire it in the second. Okay. Grab the lock in the first thread. Grab the lock in the first thread. Where is it? This one? Maybe during this one? Every 2 instructions maybe. And then test. If that's the case, maybe something like this. So running 2 instructions from thread 0 and then 2 instructions from thread 1 and then 1 instruction thread 0, 1 instruction thread 1. Basically this one first and then this one, and then maybe repeating that, and let's print the header every 6 instructions. Let's see how it goes. Okay, right. Trying to grab the lock in the first thread, but then to acquire it in the second thread. So after the first thread grab the lock, right? First thread grab the lock, the second thread try to acquire it. I assume something like that. That 0 here trying to acquire the thread, right? Or maybe already acquiring the thread. And then thread 1 trying to get the lock again. Trying to get the lock too. Okay. And then test, alright. That 0 move into the, what is it called? Critical section. That one still trying to acquire the lock. Okay. Okay, trying to acquire the lock. We release. Okay. We release the lock here. But then because we are not, what is it called? Because we are not moving the lock state before thread 0 release the lock, this test is gonna use the out of date value, right? Which means that 1 will keep spinning. Okay. Subtract that. Okay, we're going back to the top. And then this one. Okay, checking again. That's already done here, so we get the lock, right? We get the lock for thread 1. Okay, thread 0 just going back to the top. Okay, checking the lock, right? The lock still held by thread 1, moving into the critical section. The thread 1 here, moving into critical section. Okay. Alright. Thread 0 still trying to get the lock. And we just release the lock on thread 1 here. Okay, just right before we check the value of the lock or of the mutex, I guess. Of course, we're gonna spinning again on thread 0. Right. Okay, this one. Okay, this one. Moving back to the top. This also moving back to the top. Interesting. Or the acquire, I guess. Kind of the same. Right? We are moving into this instruction. And then, right. The thread 0 try to get the lock, and then thread 1 also trying to get the lock. In this case, we are not setting the lock at the same time, right? It is what is it called? It is what happened when using flag.s here. No mutual. Yeah, the scenario previously with flag.s is something like this. When one thread trying to set the flag, another thread also set the flag to 1, 2. So no mutual exclusion, but in this case we have mutual exclusion, right? So that 0 trying to get the lock, right? That 0 get the lock, and then that 1 also trying to get the lock right after that 0 setting or get the lock, right? So there is mutual exclusion here. This is the state, the previous state, I guess. Okay, and then test. Okay. Excuse me. Okay, this one. Alright, release the lock. Oh, okay, release the lock. And then after that, we are going back to acquire. Okay, get the log, portrait 1. Okay, then like this. Alright, and then doing the rest of the instruction for thread 1. Okay, so maybe does the right thing happen? I assume the mutual exclusion. Yes, at least using the, what is it called, XGHG instruction, achieve the mutual exclusion. Okay, what else should you test? I am not sure. Yeah, I mean, we already checked the mutual exclusion here, right? What should I test again? I'm not sure yet. Well, maybe let's continue into this one. Peterson.s, which implement Peterson algorithm mentioned in a sidebar in the text. Study the code and see if you can make sense of it. Peterson. Oh, the current Peterson algorithm here. Okay. Indicate intent to how to know. Oh. Is it like, what is it called? Like the ticketing system? It is basically adding the next turn for the thread. So this is the current turn, and maybe self is the self is the thread ID of the call. So self in here maybe might change when we are on different thread and not the current thread. Maybe. Okay, to Peterson. Well, let's take a look at this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.